last day, unless, yeah, I think probably we should start. Yeah, but so I'll start by announcing that we're really proud to have Lan Yang, one of our faculty, to be here. And as I was answering some of the questions that two of you asked, yeah, today is indeed the last day of a series, and I hope you enjoyed it. Unless there's a change, so actually we reserved, certainly next week we'll not have one, but the week after is a very small probability that we will have one, in which case we'll send you an email. But otherwise, this is with the last lecture of the series this semester. Okay, so again, I want to thank Lan Yang for being virtually here. Unfortunately, we cannot do it in person like in previous years. And so as I said, Lan Yang is actually one of us. She's at WashU. She's a professor in electrical engineering, and she's very highly distinguished. So she's really, what she'll talk about today is actually largely her, I mean, she's expert on many things, but really this is really her area, which is really a renowned expert on, which is understanding basically of photonics. So, and she did many spectacular things in her lab. So basically, and also before that, before she came to WashU as well. So she's actually built the first on-chip microresonator device to actually detect particles very, very accurately. She looked at what's called PT symmetric whispering galleries with exceptional points. So many of these names are sort of highly technical, but they're actually very, very important results that she actually had in her lab. She looked also for stability of these systems. So just a very, very brief biography. So she did her undergraduate in China, and she got her PhD in Caltech, and she came to WashU 13 years ago, and she's been climbing up a ladder ever since. She actually became an editor-in-chief just last year of a well-known journal from photonics. And she also was distinguished by many awards. In particular, for instance, she got the Early Career Award 10 years ago. And she actually was also awarded the Presidential Early Career Award 9 years ago. And this is a really highly distinguished award, which is awarded only to very few faculty which are showing exceptional promise. So it's the highest honor that you can give to young faculty. So without further ado, I won't take much of your time further. So as always, I mean, the format will be sort of the same, but well, I'll sort of unmute everybody. And if you have any questions, which is really pertinent to understanding what's going on, please unmute yourself and ask a question. Otherwise, you can ask questions in the chat. And then at the end of the lecture, we'll go, you can of course raise your hand virtually and so on, and we'll go through the chat and your raised hands and go through the questions. So thank you very much for being here, and Lan, it's all yours.
Okay, great. Let me share my screen. Can you see my screen now?
Yeah.
Okay, great. So it's my actual great pleasure to be here. Thanks, Zoha, to organizing such a wonderful event for general public and all students. Because as far as I know, there are some young kids actually. They are still in elementary school attending this talk. So after knowing this, I make some changes to my slides so that it can accommodate attendees at different level. So my background in photonics, I got training in material science and physics, not about light at all, until I get admitted to Caltech at Applied Physics department. I started changing I was so fascinated by light and its ubiquitous application of light. So I changed my major to photonics. And as you can see from the title, today I will help you to go through the journey to see the magic enable the light by light. So first of all, before I give the talk, I wanted to say something about the science. That is my career, especially I think it's especially prepared for kids. So why science? Is it about complicated theory, do the calculation on papers? I would say, you're partially right. Yeah, part of there's a certain branch of science that working on that, but it's not about everything about science. Put that aside. Science helps us to satisfy the curiosity for the world. It's interesting and a lot of fun, and the fun of discovering new things. That is another reason to explore science, right? In addition to that, working on science will give you training about critical thinking and this logical training. That is very important. You don't need to become a scientist and get scientific training, but it helps to give you the training of logic thinking. And also it helps us to deepen the understanding of the world. You know, you probably with a scientific background, you probably help you understand the world in a better way. And also with the skill sets you develop through the scientific research, you develop these problem solving skills to help the world. And also, of course, that will lead to technology improvement and even development of new things. And in the end, I do think working on science will give you the sense of accomplishment. That is one of many ways to enrich our life. So I hope you on the feel the same. And in the next couple of slides, I will tell you how fun it is to explore one branch of science, that is photonics and optics. So my computer is right. You know, I prepared this slide just to show our world is in dark if there is no light, right? Unless, you know, there's sunlight, it light up the whole world, right? In the daytime. And at nighttime, there is, you know, the lamps, street lamps light up the world. So we basically, human being cannot live without the world. We do need light. And that's interesting. So let's found the fundamental level to think about how we can see things. So with the human eyes, if you look at structure of human eyes, you will see there's an ancient structure we call lens. So lens is kind of a structure that will bend light going through the structure. So basically what happens is if there's a light source, which can be sun or lamp, the light bounced off the object that enters eyes can be focused at the retina. And at retina, some magical thing happen. That is, the light can be converted to electrical signal and then received by brain. And the brain will process everything to form the imaging. That is how we see things. So then here comes another thing. Then what is light, right? When I was preparing the slides for the talk a couple of days ago, my husband asked me, he said, what are you doing? I said, I'm preparing a talk for general public. He said, oh, I also want to know, can you tell me what is photon? You know, the area you have been working on. I heard it's massless. And if it's massless, can you feel it? Can you feel it? Can you touch it? I said, no, because there's no mass, you cannot touch it. And then he said, then how can you prove it exists? Because for example, even oxygen, we cannot touch it, we cannot feel it, but at least there is mass for oxygen, right? And how do you prove its presence? I think that's a very good question. So I always tell my students, there is no silly question. And many times, question motivate us to think about things, for example, like this time. For example, if you think about character or feature of photon light, photon is not a particle. It's not a physical particle. Yes, you cannot touch it, you don't feel it, it's massless. There's no electric charges owned by the photon. It's a kind of quantum, a smallest quantum light and light and other electromagnetic radiation. And then you might ask the same question as my husband, right? Who actually the PhD in computer science, just don't be shy. You don't know about things. No one knows everything. So I also think about this. Yeah, from fundamental level, how do we understand a photon? We cannot touch it, but there is a way. There is a way. What that way? That is way is related to how it was born. So how to generate light? There are many ways to generate light photon, but regardless how it works, they all converge to one mechanism, atoms. The basic physical part we know about. So we know atoms is formed by nucleus, right? Surrounded by its orbiting electrons. And there are many electrons, depending on which atoms you're talking about. Different atoms have different number of electrons. And then for many atoms, actually, there are different orbits. There are many orbits. And depending on the orbits, the electron take, they corresponded to different energy level. So the next slide will explain how light photon is generated from the atoms. And then in addition to that, I want to mention another thing. So it's different from electrons, that is physical particle. They can literally bump to each other, right? And interact with each other. A photon has no mass. How do they interact with each other? Yes, right. You're right. Intuitively, photons usually they cannot interact with each other. except for some special case with high energy. For example, one photon cannot just bounce off another one because physically they don't have mass. And then how do they interact? Normally, photons interact with each other through medium. That is why we always say when we talk about photons, when they interact with each other, we do need some medium to pass through them. Okay, so let's take a look at how photon was born. So think about atom. This is a general structure of atom, the nucleus, right? Surrounded by its orbiting electrons. And corresponding to different orbits, we use energy level to describe energy associated with different energy level. So if we think about, by chance, there is electrons at an energy state higher than the ground state, what will happen? You know, it actually has a chance to decay to the ground state. And we know the energy conservation, that is a basic law, should be followed by physical system. So where does the energy go? The atoms lose energy. And actually that amount of energy is converted to electromagnetic waves. Okay, that is how photon is born. And knowing that, okay, we know the mechanism. Then you say, okay, now I know light is how photon is born, how we get light, right? But I will still tell you, even for light photon, there are different kinds. For example, for the general light, the bulbs in your room, in your bedroom, living room, those photons have cover a broad range of wavelengths. They're divergent. That means, as shown in figure, they're in different direction. They are incoherent. When I say they're incoherent, that means they're not in pace. They're running in space, but not in pace at all. They're random, okay? However, another kind of structure we call laser actually is acronym of light amplification by stimulated emission radiation. Actually, Albert Einstein developed a theory to characterize how the laser was formed. And here is just a simple illustration showing if you have a laser in hand, it will generate a special kind of photon. Those photons are monochromatic. That means just one color. And they're collimated. They're in parallel. And they're coherent. When I say they're coherent, that means they're in pace. It's like people walking on the street, they are in exact pace. They're just like twins, everything the same. Okay, so you might wonder, okay, there are different things, but how can we generate a laser? So here we still come back to the atomic levels. If you think about it, you have atoms, many electrons orbiting around, right? And we pick 3 energy levels that can be occupied by these electrons. Okay, here comes the fun thing. If you have some pump, it can be anything, can be electric current or can be another form of light. Any energy you can put into the system. Then due to energy conservation again, the system, the materials, the electrons grab energy from the pump, from the source, then they can jump to the high energy level, right? And usually first to this E2, this energy level, they have short lifetime, like a nanosecond or picoseconds. So once they are there, they immediately decay to another level, is E1 here. And E1 normally is a metastable level. What does it mean? That means it has lifetime a little longer, much longer than the lifetime of E2. So the electron can happily stay there for a while. Okay, so basically they accumulate at an energy level E1. And the next, sometimes some of them, because energy E1, right, is still not unlimited lifetime. So once in a while, they still decay due to spontaneous emission. They just decay themselves. But here's magic. If there is what we call the stimulated photon, here means, the electrons are happily staying in energy level E1. But how come, but if there is an electron, a photon passing by, what happens is they will trigger the transition of electron from E1 to E0. And this is called stimulated emission. It's not, that means the electron hasn't reached the lifetime at E1 yet. They don't want to jump down. But however, there's something drag them down. So the outcome is when they decay from E1 to E0, because they're pushed to fall down, so to decay, and then the newly generated photon will be identical as incoming photon. They're in pace. So this is like a reinforced process, then become identical. You know, you can imagine continue this process, you will generate hundreds, thousands of millions of photons with the same pace. That's how we generate this coherent photon that can be used to form laser. And then what is the energy of this photon, or what is frequency? And this is formula to tell you, if you know the energy difference, right? Energy difference, E1 minus E0 divided by Planck's constant, that will give you the frequency of the photon generated from this process. So basically, depending on what kind of wavelengths, for example, visible wavelengths or infrared light or far field infrared, all depends on your application. You can choose appropriate materials with the right amount of energy difference that match with the frequency. So you can see laser is about a photonics device, right? But it really involve a lot of research in materials too. And also another thing I want to mention, so in addition to this kind of atomic system that have a special atomic level, right, that allow you to trigger this stimulated emission process, that is what we call the gain median. In addition to that, you do need another structure, it's called an optical resonator. Optical resonator is a special structure. It can be any shape. For example, here I show a resonance structure, which is composed of two mirrors facing each other. As long as they are aligned well, then light can be bounced back and forth. That is why we can have generated hundreds of thousands of photons, because, for example, due to the stimulated emission, right, photon generated, right? But you wanted to generate more identical photon with these mirrors, you know, as part of the resonator, those photons will be pushed back into the gain median and generate more. And when they meet the other mirror and bounce back again and generate even more photon. That is why how we started accumulate and grow the photon number within such a resonator that provide feedback, pushing the photons get back to the gain median to generate sufficient amounts of photon that can be used for lasing. Okay, so knowing the physics of laser, let's take a look at the kinds of laser that have been developed. For example, there are many materials, as I said, and one kind of material is called semiconductor. So semiconductor is special materials. In the materials, there are different bands, saying, for example, valence band, conduction band, basically just energy band, the electron can stay. And as I mentioned in previous slide, there are many ways to excite electron to higher energy level. For example, in this case, if you have a way to excite electron to conduction band, which have higher energy than the valence band, then they will decay down to when they decay down from conduction band to valence band, it loses energy. Where does the energy go? They convert it to photon. And how to generate the stimulated photon, the same as I said, stimulated process. And also, in addition to those semiconductor materials, you can use glass, for example. It's like homogeneous materials medium, but you put a little bit ions. For example, this in those transparent materials, put some active ions. For example, specifically this is transition metals, as shown here. For example, neodymium. It is doped in yacht materials. Then you're gonna get a new kind of laser, just due to, as shown here, this different energy level, right? You find a way to excite the electron in those active ions to upper energy level. Then it triggers the stimulated emission that will give you the coherent photon which will be part of the laser. And also, as I said, this is the frequency is determined by energy level between the that is involved in the stimulated emission process. And then you might wonder, okay, there's an issue. You know, it seems like there's limited choice. It seems like our choice is really limited by the materials, right? If you look at the periodic table, there are only hundreds of atoms for us to choose. The only limited energy level for us to choose. That means we wouldn't be able to have continuous tuning of frequency. We would love to have. Is there a way to generate a laser with a little bit flexibility in the frequency? Yes, we can. Another mechanism is, so the other mechanism is not exactly this associated with the atomic level. It's nonlinear effects. If you think about the energy of light photon, E, which is determined by frequency, H, and is equal to H mu. H again is Planck's constant. And then keep that in mind. Let's take a look at nonlinear process called Raman process, Raman scattering. Okay, so for example, if you think about materials within which there's molecules, many molecules, and light pass by, and those light, as I said, the molecules vibrating, for example, like this particular molecule, right? There are different ways for 3 different atoms to coordinate, have different vibration. They can stretch, they can vibrate, and they can also have symmetric stretch and asymmetrical stretch. The different ways for this molecule to vibrate. Actually, that means for the molecules, different ways of vibration corresponded to different energy level. Okay, so here comes something fun. So then you can basically define different energy level corresponding to different vibration mode, right? What happened is when light pass by, they basically interact with molecules. And many times those are elastic interaction. When I say elastic interaction, that means there is no energy exchange. They just bounce off and change the direction. Nothing happened. It's called this Rayleigh scattering. However, there is another possibility. When those lights bumped with these molecules, actually there will be energy exchange. There are 2 ways. One way is the light give energy to the molecule, or the molecule give energy to light, right? And then those processes are quite interesting. If you think about this solid line, real energy level corresponding to different vibration mode, what happens is, and then in one case, molecules will grab energy from light, and then its molecule will be excited to a different energy level. So they will change the wave of vibration. That means the light lose energy. And lose energy. When they lose energy, we know that, right? The light photon energy is determined by the frequency. If the energy change, of course, the frequency will change. So really depending on the energy difference, and okay, by the way, this is a virtual state. It could be anywhere. So basically, we can use this effect to add another strategy to tune the frequency of light. This is what we call this. That's what is what called the Raman process. So we call the photon generated from this process as Raman laser. And so this is just a simple illustration showing what happens. So very much like what we talk about in atomic system, right? But here, what is really involved is not necessary to be a real physically existing system. It could be virtual state. But it still involves exchange of energy between the light with atoms. So knowing the physics and the kind of lasers, let's see the application. In our daily life, actually, there have been many applications found by lasers. For example, laser pointers, right? That has been commonly used in classroom. And also, if you do shopping, the barcode scanner, the laser actually to scan the bars. And of course, in old times when we have CD and DVD, we use laser beam to read data encoded in the CD. And also, laser has been used. High power laser has been used to cut and welding materials. And more importantly, actually, another thing, for example, is communication. Cross-continent communication is enabled by optic fiber communication. And the fiber is just like a string of glass filament, but within which the light photon can propagate with such a structure and carry signal or information from one continent, one country to another one. So that is application we're aware of in our daily life. And also there's some cool application based on laser. And I just make a list of those because on limited time, I wouldn't be able to jump to detail, talk about each of them. For example, like LIDAR is a laser light-based detection ranging. And for example, it has been used in autonomous vehicle and has been used to do the 3D mapping morphology of an area. And also, we also know laser surgery, right? For some of you, maybe you have done this kind of surgery to correct your eye, the issue within your eyes. The advantage of laser surgery is precision. If you think about the size of physical knife and the size of laser beam, you will be amazed. The laser beam can be down to a few micrometer. If you think about diameter of human hair, that is about 100 micron. That means a laser beam precision enabled by laser knife can just be 100 times smaller than human hair. And also, oh, I put it wrong. The actual 2018 Nobel Prize in Physics is given to Ashkin for his invention of optical tweezer. And also, laser has been used for cooling. And basically, by maneuver an atom's molecules in laser, you can cool down the temperature and molecule and atoms, even down to single molecule level. And also, there's some interesting application. For example, it's called electromagnetically induced transparency. That means, for example, you have materials. Originally, it is opaque. However, if you shine a laser beam to the materials medium, it can become transparent. That is kind of magic, right? I don't have time to go through that one, but surely you can go through internet to look for more details of that one. And one last example I want to mention is the detection of gravitational waves. Scientists got the Nobel Prize because of this. That is also based on interference effect of laser beam. So a lot of things has been there. So those are just pictures showing linked to each different application. But I do want to pick some of them, for example, like LIDAR. So what is LIDAR? LIDAR is, if you think about how LIDAR works, it's actually just involves some tiny laser, some sensor. So within the sensor, it includes a laser that generates a laser beam. So laser beam shooting out. And when there is any object, for example, can be just a ground, or it can be, for example, a LIDAR system in a car, could be an object such as a car, right? Any object that can reflect laser beam back to the sensor. The sensor, because those are pulsed laser beam, so the sensor can surely calculate the time it takes for the pulse to come back. And if you know the speed of light and you know the time it takes for this single pulse to come back to the sensor, then you know the distance. So that is the principle of LIDAR. And by using this one, you can see this can do 3D mapping, and it can be used for autonomous vehicle. And these days, even it's included in iPhone for this kind of application. And also another thing I think you might feel interesting is laser surgery. For example, you might be thinking of whether you should do a laser surgery to correct your eyes, actually, to correct your eyes. Actually, last month when I was for my dental appointment, my doctor actually used a laser to cure the wounds. So that, as you can see here, I show the list of medical surgery that has enjoyed the precision of laser technology. And specifically, I want to mention technically. So how could this happen? Actually, this is because of many photo-associated effects. And so, for example, there is photochemical effect. When the laser is absorbed by the tissue, for example, or some biologic samples, there will be chemical reaction triggered. So that's called a photochemical effect. And there is also what we call the photoablative effect. This is associated to the phenomena upon the absorption of the laser beam, the tissue, soft tissue, especially tissue that is filled with water, can be evaporated. That is called a photoablation. And there is also thermal effect that is associated with some photosensitizer, for example, for some medical surgery, right? And doctor can inject some photosensitizer in advance before the surgery. And then when the laser beam shine on this part, those photosensitizer will absorb large amount of laser and turn that into heat and for certain medical treatment. There's also photomechanical effect. That means upon the absorption of the energy from laser beam, there will be some mechanical changes, such as shape or structural changes in the biological samples. And specifically, I want to talk about the photoablative effect. So for example, get back to the original slide when I talk about how we can see things, right? So basically, we can see that here we need this is tiny element within our eyes. One is a structure called lens. Another one I didn't mention previously is cornea. The cornea is also curved surface at the very front of eyes. So you can see that it is outermost lens that control the focusing of this light beam entering into our eyes. That actually, from what I found on the website, it said it contributes more than 65% of eyes focusing power. That means, for example, when we getting old, our muscle is not so good. It loses its capability to actually tune the curvature of the cornea. So that so when you're getting old, you have farsighted, right? And but for many young people, they have nearsighted. That is all because, when there's something messed up with cornea or the lens inside, instead of focusing light exactly on retina, that is critical to convert light into electrical signal that can be conceived by our brain. Instead, light will focus either before or after retina. So that is not good, right? So what that can do is change the shape of cornea to do things so that it can change the focusing power of the overall eye structure. Then by using the laser beam and by making use of photoablation, they can use the laser to achieve high precision control to reshape the cornea so that it correct your eyes issue. Yeah, so that is just one example. And I also want to mention, high power laser can have also been used for laser cutting and engraving. I guess it might be one of the hobby of one of you. Like I want to post on my group, he really enjoyed laser cutting in wood to create all kinds of artistic piece that can be used as a gift to friends and families, right? So lots of fun with laser. Okay, so much for the fun. I want to take you to go back to the old time to think about when the first laser was invented. As I said, it's all about materials, right? So if you look at the periodic table of elements, and if we choose two elements, alumni and oxide, and then you can see actually they can form some periodic structure, some crystalline structure. And this is the kind of structure actually ruby crystal. Okay, you have a structure. But sometimes, if by chance, some of the aluminum is replaced by another atom, it's called a chromium. If chromium replaces part of aluminum, then things will happen. This kind of aluminum atoms is kind of dopants. It will give the ruby crystal a bright red colors, vibrant red colors. And you might wonder why we need that. So let's surf the history. In 1960s, that is about I think 60 years ago, right? Theodore Raman invented this structure. It is composed of ruby crystal, but in cylindrical shape, and it's not a random cylindrical shape. On two ends, both ends, one end of this crystal, the cylindrical structure, is protected, is mounted with a reflecting mirror. It's a perfect mirror, so 100% of the light, when it hit the one end, it will bounce back to this ruby crystal. The other end is a mirror with partial transmission, so that we can, any photon generate can be coupled out, right? And then he used a flash lamp wrap around this ruby crystal, and this magic happens. He turn on the flash lamps, what happened? If you take a look of atomic level inside this chromium, here is energy level. What happened is The blue and green light component from the flash will excite some of the electrons in the chromium atoms to an upper energy level. And as you can see here, there is a metastable level, right? And so these electrons can temporarily stay there and accumulate there. And then if there by chance there is a photon coming by, then that photon will stimulate this stimulated emission. And due to this, and because of the mirrors, it helps to form what we call resonator structure. This stimulated photon, they will be trapped inside, bounce back and forth within the ruby structure, and then accumulate and grow from few to 100 to 1,000 or even millions. And then when the round trip of those photons, the amount of photon generated is more than what they lost due to other mechanism, then laser is generated. That's how the ruby laser was invented 60 years ago. And here, so ever since then, there have been many lasers invented all around the world, and many applications has been explored. And for me, I know some audience, the professor or even researcher, they might want to know the most recent cutting edge research. And here, I want to talk about interesting phenomena. Actually, this is kind of physics I have explored almost 20 years ago. When I attended and joined the applied physics program at Caltech, I started to know this amazing physics. This is a great example to show science most of the time is cross-discipline. And also many times I think research, if you think about the word research, is research, right? It means you search and search again. And that's exactly, I think, what we are doing. For example, if you look at this pictures on this slide, right? Those actually different buildings, architecture around the world. But there are some common feature, although they grow from different culture. One common feature shared by all the structure is all of them have circular boundary. Okay, circular boundary, that's interesting. If you think about, for example, Cathedral Dome in, for example, the one in St. Paul's Cathedral Dome in London, then you can imagine if you have a chance to go there, or actually we have also Cathedral Dome in St. Louis too. Whisper, if there's a whisper, actually, a sound can propagate along the curved wall. So that means within such an architecture structure, a single whisper can be heard throughout the gallery spaces. That is why this kind of area is called whispering gallery. And for us, working in the field of optics, the sound wave, acoustic wave has no fundamental difference from light wave, right? It's all wave. It's just in different spectrum window, different wavelengths, different frequency. And imagine if you have a way to make a structure with circular boundary, such as a microsphere, right? And then the light photon can circulate around the curved surface, just like the acoustic wave did in this Cathedral Dome. And then by doing that, light is trapped inside. Isn't that what I said about the resonator? Because I said that resonator is an essential part of laser. If you want to generate laser, you do need a structure called a resonator so that the light can be trapped inside. So it can be always trapped in the gain medium. And here comes another mechanism. We don't need mirrors. And especially if you think about integrated photonic circuits, kind of chip that ultimately, for example, one day can be integrated in our cell phone. You want this kind of resonator to generate lasing, for example, to be very small by using conventional design of resonator that is formed by mirrors aligned perfectly so light can bounce back and forth, which is challenging, right? Surely, of course. But using this structure really provided by nature, right? For example, if you heat a material due to surface tension, it will automatically melt that into spherical structure, right? So you wouldn't take much effort to turn something into spherical shape. And by doing that, you have what I called whispering gallery structure. And as I mentioned, within such a resonator, if we put a gain medium inside, then you get a whispering gallery lasing. That's another kind of laser, and in my mind, is one of the coolest laser in my mind, because if you think about the structure, it's The size can be like a 30 micron or even smaller. It's much smaller even than human hair. And however, although it's small, their application is enormous. And I'll explain how it works. And by the way, here on this slide, I show a structure that tell you how light is coupled into such a tiny structure. For example, you might say, wow, such a small structure, I couldn't even see it. How can I couple light inside? Yes, thanks for the development of nanotechnology. You can use a tapered nanofiber approach this structure. Then due to this evalescent coupling, the light can be coupled into this whispering gallery structure. And just as simple as it shows here, as shown here, within the exact same fiber, light can be coupled in and out, and for various kind of application. And this is just a panel. Really, I just lump all those rendering picture representing different application of resonator explored in my lab. For example, one application, as Zoha mentioned, is something actually we learned from our colleague Carbenda, who proposed the concept of parity time symmetry almost, I think, more than 20 years ago, saying that if you have physical system, which actually is not limited to resonator at all. He just said, if there is a physical system, if you have find a way to manipulate the gain and loss balance, you basically have a parity time symmetric structure. Within such a structure, there are many interesting physics you can explore. And then we did it, as shown here. For example, in lower left corner, you can see the resonator pairs, right? You have two resonator, and we control that exactly as Carbenda suggested many years ago. We control the gain and loss in between them. Then we found actually, for example, one application is non-reciprocal light transmission. So for example, if you have optic components, right? For example, if you think about it, that's a non-reciprocal transmission, it's important. For example, if you think about electrodiode. Electrodiode is such a component. Electric current can go through in one direction, but it's blocked in another direction. And for the same, for the photonics components, we want a similar component that allow light to propagate in one direction, but it's blocked in another direction. It's called optical diode. How to achieve that? And in our group, by using this PT symmetric pair, we did it and just manipulate the gain and loss and those parameters, we achieve those applications. There's non-reciprocal transmission enabled by parity time symmetric optical resonator. But let's focus on lasing first. Today, I think because that is the core of my talk. Particularly, there are many applications can be enabled by these micro lasers, right? Particularly, I wanted to talk about the nanoparticle application, sensing application. In the very end of my talk, you will see why I'm so fascinated by this application. Okay, so why bother, right? Why bother to invent another, use this micro laser for sensing? If you think about the object in the world, it's not just composed of object we can see, right? There are many other things way beyond the reach of human eyes that exist, and that is important, right? Like virus, DNA, antibody that are used for treatment. There's so enormous amount of things beyond what we can see, but we do want to see them, right? So it is important. You have something that can help you to see those. And in addition to this molecule proteins, I also want to mention nanoparticle, for example. Ever since the invention of nanoparticle, people are aware of nanoparticle. It has been used in many applications, such as, for example, medical imaging. It has been commonly used. It can become a routine. Nanoparticle has been used to do the medical imaging. It will indicate where tumor is. It will indicate, you can even use nanoparticle to monitor metabolism in a biological sample, right? And also, if you take a look of the components in your sunblock, you will see titanium dioxide particle is used in sunblock. You know why? Because titanium dioxide has strong absorption of UV light. So if you put that outside your skin, they will absorb the UV light for you. That is why they block UV light. And also, nanoparticle has been used for example, to strengthen the property of materials. So it has been used in, for example, this tennis racket, for example, right? And also can be used as a kind of materials medium to extend the lifetime of the battery. And also it has been used to for environmental treatment, for example, clean the underground water. It's not a lot of application. And so there's one physical parameters you want to know about the particle. For example, here on the left side of my slide, it shows a series of properties that are affected the size of nanoparticle. So that means, yes, on one hand, we can generate and manufacture hundreds, thousands of different kind of nanoparticle, right? But if those properties can be changed by the particle size, then you do want it to have something, a sensor that can measure the size, right? And how to do the measurement. So that's something I want to talk about. So this is what I said, whispering gallery light. We put some earthing ions, real earth ions, into such a tiny structure. And then you can see the green light, the purple light can be generated inside, the green light can be generated inside, right? And here I show two movies, actually, showing the side and top view of a tiny structure. I wanted to mention here, those, or you can see that, but their actual size is way much smaller than human hair. We need to enlarge the picture in order for you to see that. The green light is generated within this whispering gallery resonator. And that is direct evidence showing how the laser was generated inside, right? And once we have this micro laser, then you might wonder how to use that for sensing. Okay, then one other thing I want to educate you is you need to know what is mode. So light can propagate inside, right? But it's not like a randomly inside. If you think about, for example, I put a bunny here. For the bunny to travel from A to B, the different way, many different ways for the bunny to choose, right? And that is what we define mode here. When the light finishes a round trip within such a circular structure, the many physical paths that can be taken by light. Different paths, for example, as shown here, those are real experiments from the lab. So you can see the different patterns, right? Different patterns corresponded to different paths taken by light, and that corresponded to different mode, okay? And then you might wonder, okay, what is reality? Yeah, here we go. Here I show a movie. It is a tiny microsphere, smaller than the human hair, and you can see different kind of patterns can be excited, right? And different patterns corresponded to different mode. And how we could quantify that? Actually, it's quite simple. If you look at a nano waveguide that is used to couple light in and out, if you look at the output side, when the light is trapped inside, of course, you wouldn't be able to get a transmission, right? That is why you see a dip, because that is the position where the light is trapped inside. And we found that is 10 years ago, when I actually worked with my first graduate students, we found when there is a surface defect or nanoparticle attaching to the surface, there's a single resonance will split into two. That's interesting, right? It's split into two. And we even have algorithm developed so that, for example, this real experiments, single nanoparticle adding to the ring, one split into two. And my group also developed the algorithm. We can do curve fitting to do the curving to match with split modes. And from the curve fitting, we can tell you exactly the size of the nanoparticle. So that means our tiny whispering gallery sensor will achieve not only detection, but also quantitative measurement, the size measurement of nanoparticle. And we also did some fun experiments. For example, in addition to do this calibration by using standard polystyrene nanoparticle, we purchased from vendors. We also purchased this inactive influenza A virus. That's something we care about, right? Every year we need to take vaccine to avoid it, to protect us from cold. And here we tested this influenza A virus. You can clearly see whenever there is nanoparticle adding or passing by the laser, they will see changes in those mode splitting. And we clearly demonstrate that. And I also want to tell you the average size of the influenza A virus is around the 60 nanometer. It's nanometer size. So this is just, we use scanning electron microscope, an expensive bulky instrument, but it's a standard instrument that allow us to see nanostructure. And this physically shows that, yes, those nanoparticles did land on the ring of the sensor, and we can see, and we can measure that, although we cannot see it. So here's the take-home message. If you have a tiny whispering gallery sensor, right, whispering gallery laser, when there is nanoparticle adding or passing by the resonator, the laser beam will split into two. When I say laser beam split into different frequency, that means different color. Then in the spectrum, we just need to analyze the location, the appearance, that means the shape of those two lasing lines. Then we will be able to detect and measure the size of this nanoparticle using our sensor. So as I said, in the very end, I will show you the motivation, why there are many applications, research explored in my lab, why I single out this nanoparticle application. Yes, I guess here today, I guess everybody know this particular nanoparticle, right? It's coronavirus. This is tiny structure, it's nanostructure. We couldn't even grab it, but it really disturbed the whole world. And our daily life is seriously affected by this virus. It is a virus, we don't know its chemistry property, but at least from our point of view, it's just yet another nanoparticle. So we are wondering, yes, actually, is that possible that we can use this chip scale nano sensor, that one day we can turn that into portable system, really portable system, and they can install it in many, like a public space, airplane, and even at home. And maybe, for example, now we can only do detection, nanoparticle, right? How to achieve selectivity? Because you might argue, you know, there are many kinds of nanoparticle, even like a polling particle, right? In addition to the coronavirus, can we come up, the scientists come up with a strategy that one day can make use of the tiny micro laser to do detection? And to do detection in a way, not only just detect something, but also tell us what it is. I guess if one day we can achieve that, then this will be another great application of scientific research. I think, personally for me, I think that is a motivation for me to really work on science. Because for me, I think science, for kids, I would say science is fun, but for us who consider scientific research as our career, I do think it's our responsibility and mission to work on science, to develop something that one day can help the world. One day that what we do can make people's life better. I think that is our final goal of my research. In the very end, I wanted to thank my students. I have many students, but particularly Chengqing, Zhou Tian, and Max. They really helped me to prepare some of the slides. And I also thank my daughter, Sophia, who added some artistic elements to my talk. Hopefully that helped to make you feel the slides interesting to you. And in the end, I thank you for your attention, for spending 1 hour with me during the weekend. And for more information, you can visit my website. And thanks a lot.
Thank you very much, Lan, for a very illuminating talk in many more ways than one. So there are a few questions in the chat, which we'll get to. And also, if you want to unmute yourself and ask questions, please do that. So actually, quite a few remarks and questions. Okay, so I'll start. Maybe I'll adjust chronologically. So Ken, I mean, did you want to ask your original question? Okay.
Let's see. Early in the lecture, you put up a slide with it looked like electron energy levels.
Yeah.
And there were numbers associated with that, and I wondered if those numbers, first of all, are those numbers basically represent the different energy, the amount of energy quantitatively.
Good question. I'm sorry. Yeah, no, they didn't associate, not about a specific energy. They're not.
Oh, what are they then?
Those are just like a symbol to those. For example, KLMN, just symbol to represent different orbits. So we're not say this orbit, that orbit. We will just say KL. When we say that, the people know we are referring to which energy level we're referring to.
Okay, and the numbers don't mean
electrons,
anything then?
Number of electrons.
Number of electrons.
Yeah.
What? Okay. Well.
Yeah, for example, for a specific orbit, you couldn't have unlimited electron there actually. For every single orbit, there are only a certain number of electrons. That is why, for example, commonly, right, all the electrons should prefer to stay in ground level. But in reality is there's only a certain number of electrons that can be occupied by in certain level. That is why actually we can count. If you, for example, if you give a physicist the total number of electrons, he will get back to you to exact electron in each orbit because he can do the round calculation.
I see. Okay. All right. Good. All right. Thank you.
Thank you.
Great question. Actually, there was quite a few remarks and questions, but I guess they were answered by other people. But there was one at the end by, I should know your first name. I'm sorry about this. By A. Bloch. Did you want to ask it yourself?
Yes, Alice. Well, I had
Alice,
read somewhere that, no, thank you, that there's potential danger. We do not know the effects of nanoparticles that can, go through the skin and into the cells, or that can get into the environment. So I was wondering, I could see the potential for good, but I was wondering also on the other end of the spectrum, can they do harm that we don't understand?
Yes, that's a very good question, actually. So it's for nanoparticle, right? When I only show the great things about nanoparticle, but you definitely bring up another issue. Actually, that is even for National Science Foundation, they sponsor a lot of research to study the harmful side, the negative side of nanoparticle. So it is a fact we should pay attention to. That's actually another motivation for all application, all nanosensor. We can do some systematic investigation, for example, to see how the property of nanoparticle changes, how it can how this effect changes based on local changes of environment. Yeah, it's not all positive effects. There are many negative effects we should pay attention to. Yeah, that is why there's an urgent need for this nanosensor that can characterize those nanoparticles. That's a very good question.
Thank you.
Thank you.
So other questions? There are lots of remarks in the chat, but actually not really questions. But we'll go through them briefly. Other questions?
I have some technical questions, so Herbert, I'm not sure.
Of course. Go ahead. Absolutely.
So there is something interesting I found interesting about the PT symmetric, case we're talking about. So I wonder, really, I mean, that demonstration you were talking about, how much quantum mechanics is there, if any, okay? Or it's that realization is more just a proof that there is, some non-Hermitian Hamiltonian that essentially is classical electromagnetism written in a different way. And that's what you are showing, more than, PT symmetric quantum mechanics. So let me ask you the question differently. So if you take the same device and you start reducing the number of photons, okay, do you see eventually that there is a breaking of, PT symmetry in your experiment? And not just, classical light.
So actually, the periodic time symmetry was developed in the context of quantum mechanics. So I would say my answer to your question is yes. But as specifically how in the behavior in PT symmetric regime is not clear, but I can bring your attention. Recently, there have been theoretical study to show, for example, there's a PT symmetry system, right? One phenomenon I didn't mention is a spontaneous phase transition. So in the PT pair, there's a PT symmetrical phase, there's a PT symmetry broken phase. So this different phase is marked by phase transition point. That phase transition point is called exception point. And till now, there is no experimental demonstration yet, but there are some theoretical studies showing that, for example, like entanglement of photons and the lifetime of those coherence of photons will be affected at exception point. Yeah, they have been studied, theoretical studies showing that. So I do believe my answer is yes to that, to your question. But as for specifically how when we decrease number to a few photons, how those entanglement will change, squeeze of light will behave, I think that actually is a study my group want to explore in the next few years. It's definitely an exciting direction we want to explore.
Yeah, thank you. I mean, that's what I wonder, because you see, I mean, that is the real interesting question for anybody that is interested in quantum.
Yes, and as far as I know, DoD recently have a program supporting $1 million of research to study how the quantum system is affected at exception point. Yeah, actually I think it's on the way. So probably in 2 years, I may come back to you with a more specific answer with more experimental evidence.
Thank you.
Thank you very much. Actually, we have another question by Leo Hong. Do you want to ask it yourself?
Is there a difference between infrared light and the heat?
What?
So the question,
light and heat?
Infrared light and heat, exactly. That was like that.
Infrared light and heat?
Okay, so can I repeat the question? So you're wondering how light can generate heat?
I was wondering, is there a difference?
Is that a question?
I was wondering if there was a difference between infrared light and heat.
Oh, there's difference between light and heat. Okay, simple answer is light can be absorbed to generate heat, but physically there are different things. Let's say this: heat is something a kind of phenomena associated in the materials, right? But the light can be separate from that, but the light photon can interact with materials to generate heat. So you can think about the light and heat, a different form of energy. Did I answer your question?
Yes.
Okay, thank you.
Thank you.
So thank you, Leo, for asking that question. Really appreciate it. And actually, we have another question, but by Jay Burns. I mean, Jay, do you want to ask your question?
Okay. What is the highest frequency solid state laser that's been highest frequency wavelength laser that's been achieved reliably, and what are the materials that are used to compose it?
You mean highest frequency?
Highest frequency light, yes, or highest frequency. What highest energy particle, highest energy solid state laser.
Okay, if you call the laser, I would say that could be down UV light, for example, almost already approach the limit. Yeah.
And what materials are used to compose that solid state I'm talking about?
What particular materials? So yeah, for that I'm not familiar with which materials, but I do know it has been demonstrated. Yeah, I'm not familiar with the specific kind of materials that have been used to generate this UV light.
Okay, thank you.
Well, thank you, Jay. Thank you very much. So, other questions that anybody wants to ask?
Hi, Lan, Joe Zanley. How you been doing?
Hi, good. Nice to see you.
The last time I saw your daughter, she was in a little cradle that you were carrying around. So she was a baby. So now she's in 9th grade, huh?
Yes, I wonder whether you can hear the screaming in the background. Actually, I can hear that. I hope you don't.
Wait a minute, she's in 9th grade and screaming?
No, my that one, 9th grade is very quiet, and my youngest one is
Oh, okay.
still 3rd grade. Can still make a noise for me.
Okay, so here's my question is, were you at the colloquium when Marlon Scully was in St. Louis?
Mm-hmm.
So
I was
after
not.
that,
Mhm.
oh, you were not. Yeah, I didn't think you were, because I don't, I was asking him about it. It's in his book on quantum optics. I apologize, this is more of an advanced question. And I was talking to him about lasing without inversion. Okay, I assume you're somewhat familiar with that topic. So I've never quite understood it. Number one, he tried to explain it to me. I still didn't get it. But it's supposed to be related to electromagnetically induced transparency, which I don't see the connection there. But have you thought about lasing without inversion and how you might implement that with your micro resonators? How you might have you ever thought about it before, number one? And number two, have you thought about it maybe with in terms of micro resonators? How would you do something like that? Maybe just throwing out ideas.
Okay, that's a very good question. I'm at the same, you know, as for its correlation to EIT, electromagnetic induced transparency, I'm also not aware of that. But I did think about what you mentioned. Whether we can, when I give lecture about laser, right, I always say we need a population inversion, we need a gain median, we need an optical resonator, right, provide feedback. But later I realized, are they truly the essential part? Most of the time we do need those, but I don't think you do need to have such a nice resonator in order to generate laser median. For example, there is research from by a group of research in Yale University. They use random median. It's definitely not like
I was going to ask you about random lasers too, random medium.
Yeah, random median. Yeah, laser was generated inside. And normally we think you should have population inversion, so you can have this net number of photons generated, right? But however, if you just think about the physics, right? As long as the atoms, even before they reach population inversion, by the way, for the audience, I want to tell you what is population inversion we're talking about. Population inversion means when we say the atomic level, right? You want to generate laser. You know, if you have more ions in the ground level than what in the upper energy level, you wouldn't have laser. You need to have population inversion. That means you have more number of electrons in higher energy level in order to generate a net number of photon. So that is the requirement. And now the question I'm trying to answer is, do we need that? But if you look at the physics here, right? Actually, as long as you have electrons in upper energy level, and as long as there's incoming photon coming by, they will trigger stimulated emission, right? I think then it's down to the strategy. Can we make use of those stimulated emission, this photon generated from the stimulated emission, and put them together to form this coherent laser beam? So I would say my brave answer now, I haven't done it. My group hasn't done it. We always see lasing once it reached the population inversion, but I do think it is possible. And probably
yeah, I've always heard it's more efficient. It's always more efficient to do it with population inversion.
Exactly. It's about efficiency. That's true. Yeah.
Okay. Yeah, I've also read that it has something to do with when they're building their structures or modifying the absorption coefficients in it, but I don't fully understand it yet. Every time I go to read it, I get caught up in too many diagrams. All right. Well, it's good to talk to you again. You take care.
Yeah. You know, when COVID-19 is gone, stop by my office. Okay. Let's have some chat.
All right. Yeah, I'd like to do that. Take care.
So thank you for the question, Joe. Are there any other questions?
Yeah, I'd like to ask one.
Go ahead.
So once we have these autonomous vehicles around with LIDARs all over, they're not visible light, is that right? So we won't really be aware that we're not going to have lasers flashing around all over, are we?
Yes, you're right. I believe, yes. I think it should be some visible light.
Just a long wavelength?
And that's a good question. I'm not sure of which. Sometimes for industry application, I guess they care about the cost. So I guess depending on vendor, they might choose different wavelengths. But surely will be wavelengths beyond what we can see, as you said. It will be a big concern if someone flashes light, you can see that. Very likely to be far infrared, yeah.
So if I can match my question, David, actually there are a few remarks. Maybe you can read it yourself, of course. But in terms of questions, I mean, do you ever questions? Okay, I guess not. I mean, so I can just quickly read off some of the comments in the chat. I guess you can see it yourself about laser surgery and if it's painful or not. Also about chemical. Comment by Frank Starry about chemical lasers. Also, Brian Marston, Whispering Gallery at Union Station, that he actually has a link there. And also by Frank about using X-ray lasers for anti-missile defense, which are all, of course, very interesting points. So I guess if really one last chance. Absolutely, go ahead, Ken. Sorry.
Yeah. This laser-induced, electromagnetically induced transparency. When can I turn that on and, walk around and not be seen, that sort of thing? Are they making progress? Are they making any progress? Are they doing any cool experiments and show what's the state of that, basically?
That's a very cool application, right? But I think it's unlikely will be used for that particular application. I think it's let me see whether I have some slides here. Actually, I don't. Let me bring the other slides I have. So this EIT, make something invisible, right? That's something very interesting. But this particular EIT, the main application is not for that. It's more for optical memory, quantum memory, slow and fast light application. The reason is because when the light experience is a EIT phenomena, there is a drastic changes of dispersion curve. When you see dispersion curve, that means one example. Let me explain what is dispersion first for general audience. So for example, the reason we can use a prism to separate white light, for example, if you shine white light on prism, the color will separate, right? There were different color coming out from the prism. That is because within the materials medium, different frequency see different refract index. So refract index material is wavelength dependent. Okay, that is one thing. And another thing we want to remember is the speed of light is not just speed of light we think. We always think when we say speed of light is 3 times 10 to 8 meters per second. That is true for vacuum. When we talk about speed of light in materials medium, it is a vacuum speed divided by refract index, right? So when we talk about dispersion curve, that's just a curve showing how refract index changes with frequency. And if you take a closer look at EIT phenomena, it will tell you actually when at this, so EIT is such phenomena. When the light passes through materials medium, it is strong absorption. So if you look at absorption spectrum, it's a strong peak, right? However, when you use another beam, it's like a control beam. So EIT involve 2 laser beam, 2 light beam interacting with 3 atomic system in the materials medium. What happens is the reason there is absorption is because the light coming through the materials matches with the energy difference between 2 energy level within the materials. If we get the match, so you can surely those electrons will absorb energy, right? Jump to the upper energy level. Then they're required to decay and turn into heat or other things. So that is why there's strong absorption. However, if you have another laser beam maneuver the electron occupation, what happens is for those initial photon light beam, they wouldn't have a chance to interact with electron anymore. So then the whole thing sounds transparent. And if you do some calculation, you found dispersion curve will change drastically. When I say dispersion curve means refract index will change a lot in those transparency window. When the dispersion change, refract index change, then if you think about speed of light, that is big change in refract index, right? The effect of refract index, then that means speed of light is changed enormously, right? Speed of light is not 3 times 10 to 8 anymore. And there was actually some experiments demonstrating that it could be decreased down to like 100 meters a second, and effective, of course. So that is, and you can imagine when the light is slowed down, then it becomes a memory, right? Memory component. And that is why actually they have been experimental demonstrations showing EIT phenomena for optical memory. And it has been demonstrated for quantum memory too. So because this kind of phenomenon also apply, naturally it involves light interacting with atomic system. It is quantum system. So naturally, even you decrease this whole thing into photon, several photon level, it's still, what I said is still true. So the main application is optical memory, this quantum memory. Yeah, a slow and fast light application, not for visible things, because I said we involve 2 laser beam.
Okay. All right. Well, thank you. Appreciate it.
Thank you.
Thank you, Ken. Other questions? Okay, I guess if not, then let's thank Lan for a fantastic talk. So thank you very much, Lan. And unfortunately, this is probably the last talk that we will have, unless things will change. I mean, not COVID-wise, but in terms of, hopefully, of course, also that, but in terms of somebody else, in which case I'll let you know. But otherwise, by default, this is the last lecture we'll have this semester. So thank you much for all the questions and participating.
Yeah.
And see you later on. And thank you, Lan, really very much for a great talk.
Thank you. Have a good day for everyone.